Well, hello there. So today's video is on Hertzsprung Russell diagram. This diagram is used to compare the magnitude of intensity, luminosity, and temperatures of different stars in our cosmos. This is a graph which has been made on the data that has been collected over the years about the different stars in our cosmos. So this graph shows a relationship between a star's brightness and its temperature. And it helps astronomers to understand how the stellar evolution works, how the star moves from one stage to another stage, and how the temperature changes. Now, let's just get started. Okay, so the first thing that we need to know is what are the position of different kind of stars. This is an actual diagram, HR diagram, but you clearly don't need to know that. But what you need to know is the position of different stars at different stage of their life. So white dwarfs, as you can see, is somewhere here. So this is white dwarfs. This is the main sequence. Most of the stars, they spend most of their life in the main sequence. This is when they're using up all their hydrogen. Hydrogen is not finished. When they're burning up all the hydrogen, they are in the main sequence. Okay, no, I'm not telling you that right now. So this one is giants in this area, and this one is supergiants. Now, as you can see, the left side of your graph is blue in color. So blue means the temperatures are higher. Red means temperatures are lower. Remember, wavelength is inversely proportional to temperature. So higher the temperature, less would be the wavelength. And red color has a higher wavelength. So sometimes on the graph, you will have these numbers, alphabets, O, B, A. These are spectral series that correspond to a particular temperature. So these are the temperatures. So what you need to know for your exam is what do you have on x-axis, what do you have on y-axis, and the positions of different stages of a star's life. Also, you need to know which area the star would be brightest. So the stars which are in this area would be brightest. The stars in this area would be less, so equally bright, because they're almost at the same level. But these stars have less temperature but equally bright. These star has higher temperature but equally bright. Now what would happen, why these two are equally bright even if their temperatures are so different, is now then the size. Obviously these are huge in size, and that's why they have higher intensity. Okay, now another simple diagram to make you understand. So you see the main sequence. Let me try and make a diagram for you to understand. So you have main sequence stars somewhere here. So this is the main sequence of the stars. You have white dwarfs in this area, giants in this area, and supergiants in this area. Here you have absolute magnitude that helps us to understand what is the brightness of a star without considering the distance, how far it is. We're just interested in the absolute brightness of the star. It follows a logarithmic scale. That's why you see these numbers plus 15, plus 10, plus 5. The one with minus 10 is extremely bright. But why? How come negative? Because it's a logarithmic scale. And if you are too curious, I can give you the equation. But this just tells you that it is the brightest. So brightness increases. Okay, as you can see on the right hand side, the sun has one luminosity, and if it is 10,000 corresponding to this, that means the brightness is increasing. And on the x-axis, on the horizontal axis, the temperature decreases. It's completely against the way you've done the graphs, so do not get confused. The M series would have the lowest temperature and O series would have the highest temperature. Okay, so axis scales ranging from minus 10 to plus 15. Where would be the plus 15? bottommost or the topmost? So bottommost. So this will be plus 15 and this would be minus 10 because minus 10 is highest brightness, and then the temperature ranging from 50,000 to 2,500. So this would be 50,000 somewhere here, and this somewhere here would be 2,500 Kelvin. Lower temperature decreases, and this would be O and this would be M. Spectral class. So spectral class and temperatures on the x-axis, and on the y-axis or the vertical axis you have absolute magnitude. I also have, see, can you see, I put the temperature here, not my, I have taken this picture from Google. So the temperature is on the top, but choosing specifically this picture, that is me. Out of millions of pictures, I chose this picture, so that's credit goes to me. So the temperature here, and then the spectral class here, so you can see how the temperature is decreasing and how the luminosity is increasing, or the brightness is increasing as it goes up. Okay, so that's your HR diagram. Now, this we need to know for the example. Where is the position of the sun? Has currently sun used up all its hydrogen, or is still using? Where is it? Let me just try and make it here again. So just to make you remember, what do we have here? We have absolute magnitude or luminosity, just writing the short forms. And then here you have decreasing temperature. Okay, here you have main sequence. Okay, upon my drawing, here you have white dwarf, giants, and then supergiants. So sun is somewhere here. It has around 6,000 Kelvin temperature, so somewhere here. And after this, why is it here? Because it is still using up hydrogen. It has not finished all of its hydrogen. Path of a star similar to our sun on the HR diagram from formation to white dwarf. Say, okay, again making, I'm just doing it so that it helps you remember. Okay, just sometimes you do it more than once, it helps you remember. So this is giants and this is supergiants. The sun is here. So where would it go? From main sequence, it would become a giant. Okay, once all the hydrogen is used up, it is going to start expanding in size, and then sorry about that. So right now the sun is in main sequence. It is going to go to a giant, it's going to become a giant, and then it's going to become a white dwarf. So that's the path followed. Why the sun is here? Temperature is around 6,000 Kelvin, and luminosity is with absolute magnitude as 1, which we compare everything to our sun, so that's why sun is taken as 1. So sun is going to stay in the main sequence for around 10 billion years, because that's the time we are expecting it'll take to consume all the hydrogen it has. Fairly constant temperature and constant luminosity. And then there will be slight upward movement as luminosity, because it's going to slowly increase because of the gradual increase in the core temperature. And then it's going to move to red giant phase. Once all the hydrogen is used up, it's going to move to red giant phase here. So this is red giant. This is supergiant. We don't need to know this right now. So it's going to move to red giant phase once all the hydrogen is going to use up, because then the core will contract and the outer layers of the star is going to expand. It is going to become cooler on outside, but much more luminous. That's why it's gone up on the graph. See, it's moving up. So this location is up, so it has higher luminosity. You need to write these in your exam. So it has moved up. Why? Because it has become slightly brighter. Now, yeah. And why does it move to the right? Because the temperature has become cooled down. It has become more luminous, but it has cooled down. Now, once the helium starts burning, and then core of the burning helium, it stabilizes for a short period of time, and after that it will start moving towards the left, because helium is going to start producing more and more heat, but it stays same luminous, and then Once the outer layers are ejected because of the gravity, the core will condense and condense because of the helium burning. The outer layers would be rejected, and the luminosity would drop drastically, and it'll come down as a white dwarf. So it'll move down and left, hot but dim. So it's hot but dim. Okay, cold but bright. Okay, that's it. Sometimes you have to just explain how it moves on the HR diagram. Then you don't need to explain the life cycle of the sun. You just need to know how it moves. So it moves from main sequence after burning the hydrogen to red giant, expanding of the outer layers, becoming brighter but cold, cooling down. Then it comes to the white dwarf, becoming hotter but less dim. So you're explaining HR diagram position, but you're not explaining the life cycle. Now, let's do some exam questions. State what is plotted on each axis of a Hertzsprung Russell diagram. Let's just pause and try to answer this. Try to make the diagram in your book and then state. That's not required for your exam, just to make you remember. All right, now check. So y-axis, you should have luminosity or absolute magnitude. X-axis, surface temperature or spectral class. Sometimes color is also given. All right, next. Describe the main features of the HR diagram. Pause and write the main features. What is it? The main features, whatever comes in your mind, write it down. Pause it. If you have done it, then check. You need to describe to them, you're describing main features, you're describing main sequence, where is low temperature, where is low luminosity, where is giants, what does giants have? They have high luminosity, low temperatures, white dwarfs, which is low luminosity, high temperatures, any of them. Okay, next to the next. A star is hot but has low luminosity. Now, reading this first line, you should think, where could the star be? Could it be on the left bottom or on the right bottom? It has low luminosity, but it is hot. State where it would be found on a chart diagram and identify the type of star. Pause it and try to write it. You can go rewind and try to write the answer. If you've done that, here's your answer. Lower left region of diagram identified as white dwarf. Lower luminosity despite high temperature implies the small size. That's the type of the star, small white dwarf. Explain why red giants have high luminosity despite having low surface temperature. Again, pause, try to write answer, think where is red giant on the diagram, and then try to answer it. Okay, now you need to link this one to Stephen's law. Remember, we did that luminosity is sigma a t to the power 4. So those giants have low surface temperature, but they have larger area. That's why the luminosity increases. Depends on this first thing. They have large radius, large area, hence larger luminosity. Okay, I don't know. This is a horrible thing. This is what it is. I don't know why it must have auto-corrected while I was writing. That's the formula. Okay, describe how the position of a star on HR diagram changes. Now, this previous question was checking your previous knowledge plus HR diagram. So Stephen's law plus HR diagram. Let's see this one. How the position of a star on HR diagram changes as it evolves from main sequence to a red giant. So if it is going from main to red giant, how the position is changing. So you need to talk about, okay, I'll just stop. You need to pause the video and write and then check. Okay, why it evolves from main sequence to red star. Now they have to talk about where is it moving on the HR diagram. Moving because it's asking how the position of a star on HR diagram is changing. So you need to check, say move up and right. And then because why is it moving up and right? Because the temperature is cooling down, and because it is becoming larger in size, luminosity is increasing. All right. Okay. All right. This is horrible. Let's just correct it. Let's just do two stars have same surface temperature. One is much more luminous. So same temperature, imagine you're drawing a vertical line on an HR. So on an HR diagram, you're drawing a vertical line because the temperature is same. One is more luminous than the other. How this difference can be interpreted on the HR diagram. I've drawn the diagram to help you understand. Try to write your own answer. How this difference can be interpreted using HR diagram. Here you go. Same position, horizontal. No, this is same temperature, so same position vertically on HR. Sorry about that. Vertically on the HR diagram. More luminous is higher vertically. Okay. Difference due to radius and surface area. Okay, did I write this right? Same position horizontally. Oh yeah, sorry, it is right. Oh my god, it is right. Horizontally, it is in the same position. So it is at the same position. So, but vertically, the higher, the one which has more brightness would be higher. Why? Because it would have larger area. Remember Stephen's law again. If the temperature is same, the only factor responsible for luminosity would be then area. So why this would be higher? Because it would have a larger area or larger radius and then high luminosity. And then you could say then one is in main sequence and another one is giant, obvious reasons. Okay. Next one. How the HR diagram can be used to compare and classify stars, including reference to different region and stellar properties. Now, try to compare. So you're comparing what? You're comparing luminosity and temperature, and then classify main sequence, white dwarf, giant, red supergiant, and include reference to top, bottom, top left, bottom left, right, top right, and then the stellar properties. How bright the star would be, okay, how far would it be, how hot would it be. Try to write the answer, pause it and write the answer. If you've done that, check. Main sequence identified and described, giants, supergiants identified and described. Links between position and properties. If it is at top left, it should be higher temperature, high luminosity. Bottom left, low luminosity, high temperature. Explanation of trends, what is happening on the diagonal main sequence, because they must be using hydrogen, stable, clear, coherent explanation using correct terminology. Okay, that means you should have said the word like luminosity, temperature, main sequence, white dwarfs, giants, supergiants, all of that. Okay, so that's about HR diagram. It's a very good diagram. I really like it because it is such a nice thing to understand where a given star would be. So if I see a star here, that simply shows. Go ahead, you tell me. Yes, white dwarf, very high temperature. Yes, less magnitude as compared to something that might be here, which is a supergiant because it has a huge magnitude of luminosity, but the temperature is not that high. Right? So well done. Keep revising and keep learning. Thank you.